The objective of this video is to try and understand the solution workflow in Icepak Classic. We will modify simple solver settings and create different monitor points, check solution convergence, and verify mass and energy conservation, and also post-process the solution. Look at the solution using a cut plane solution at the faces, and also look at various plots. As you can see in the model, we have uh, electronics component which is inside a box, and there are two fans which will be blowing air on top of this electronic component. There are chips which are going to generate heat, and we will look into the solution to see what is the maximum temperature um, uh, that the solution will compute. We start by changing some preferences. Edit preference, display, and you can change the color legend format to float and set the numerical display precision to 4. Also, the screen up direction is in the positive Z direction, that is this direction, and the background style can be changed. So let's look at color 1. Right now the background is all white. You can change that to any other color, but I think white is better. Let's keep it white and save it for this project. We'll also try and color different objects differently, and to do that, again, you go to preference, go to object types, and from here you can change the color and the width of the object. So if you want to change the width of the cabinet to a thicker material, you can change that. You will see that the width changes. You can also change the color and this object, and you can see how the width changed. Now we will quickly generate a mesh. Go to mesh. You can see the mesh is complete and generated, and the number of nodes generated is 66,562. Let's change some basic parameters. Go to problem setup, basic parameters. We'll be solving the flow and temperature. Radiation is off at this time. We'll be using zero equation turbulent model and not solve for gravity. Accept. We go to solution setting. Number of iteration we will run is 400, and this is the convergence criteria. Parallel setting, we can use serial or we can use parallel. In this case, we'll use parallel. Let's use 4 processors. We're not going to use the GPU computing, and accept. Advanced setting, we're not going to change anything in the advanced setting, and we'll keep everything to default, so you can just reset it to default and accept. We can create monitor points for these points. So let's select all these points, remove the board, and you can just drag and drop them into points. So this will automatically create monitor points for at the center of the specific location. Make sure not to create more than 10 because that has an impact on the solution speed. Now, if you want to see any one of these points, you can double click on them. You can see the location, and you're going to monitor, it's going to monitor the temperature, and we don't need to monitor the pressure and velocity at this point. So we'll just click down. At this point, we can start setting up the solution. Let's write the name, convection. No, there's nothing to change in this section. The results, we are going to write the overview of the results when finished. So that tells me what's the final convergence like. At this point, we can just start the solution. You can see that the calculation is converging monotonously. The residuals are falling. And on the right hand side, you can see what is the computer temperature at different location. The calculation is completed 400 iteration, but as we can see that the temperatures have still not become constant. So we will modify the solve. This is select the data that we created right now. So you can see the calculation has started from the last computed data point. And as the collision proceeds, we can see that the temperature variation is not significant. So at this point, we can consider the solution has converged fairly. And with that assumption, we can terminate the calculation. Once we terminate the calculation, the solution overview will be displayed. And you can check in the first section about the mass and volume flow rates. So this is the specified value, and this is what has been calculated. So you can see that the calculated value for the fan left and right is pretty good, and the overall calculation within the cabinet is the addition of these two. At the same time, um, the specification in terms of kgs per second for fan left and right is well calculated. Below, you can see what is the specified and calculated value for the heat inputs for different cell zones. Finally, you can sum these values over here to compute the overall power. So if you sum it, you can find that this value should be close to uh, the value that has been specified, and this value, that is the mass conservation, should be as close to zero as possible. So now we can see that the solution convergence is good. Let's close this value and let's post-process some data. First, we will create a face object, the based temperature plot. So click on the face object and you select different areas where you want to. So you can control select different regions. Click on show contours, click on parameters, select the uh, scalar that you want to display, not the global limits, we want it with local limits. So this object, so you have to apply the objects, and once you apply, then you apply over here, and this value will be displayed. So now you can see how the temperature plot looks like at different objects. We can further add more to it, like we missed these two, we will accept and update. Now you can see the full temperature profile. You can also control and use your center mouse button to place the contours scale at different location. Now you can activate and deactivate this view by just right clicking and clicking on this active deactivate. So once you deactivate it, it goes into the inactive part. Now let's create vectors. You go click on the object face again, name it as vector. Select the objects, select cabinet, click on show vectors, parameters, velocity magnitude has been selected for color. Using this object, apply and done. You can see how the vectors look like, but we also want to see the vectors in these regions. So let's modify it a little bit. Let's add the heatsink to it. Date, date, done. So you can immediately see that the heatsink is receiving non-uniform velocities. You have much higher velocity or flow through the heatsink on the upper side, that is in the positive y-axis or y-axis side, compared to on this lower side. So essentially, this will immediately lead to a higher temperature on this side compared to the lower temperature on that side. So if I go back and reactivate the temperature plot that we created, we can see that the temperature in this region where the vectors are higher, or the velocity of where the flow velocity is higher, is lower compared to this region where the temperature is much higher because of the lower convection. Let's deactivate the face again. Also, you can change the way the vectors look like. So I go to vectors, go to parameters. You can change the arrow style, different object. If we select 3D arrow object, you can see. So these are just user experience improvements, which you can use to create different type of vector products. Now, let me deactivate this. Let's create another one. This time we will be creating tracks or particle traces. Particle traces, select the object. Let's select a group, which is the fan group that we created earlier. Accept it. Select temperature as the color variable. We want uniform and we want 50 point per input location. So there will be 50 tracks per fan. to use the local object, and you can change the marker type. So in this case, we will be using marker cone, and we set the size to 2 and width to 3. Apply. You can see how the flow looks like as the fan pushes it through the system. And we can immediately see why one side of the heatsink is receiving more air flow compared to the other side. Now let's deactivate this and create a cut plane. To create a cut plane, you will use the plane cut tool. You can create a cut plane just by clicking on different location. So let's select horizontal screen select. Just position it properly. Select horizontal screen select. And left click. Once you have selected that location, activate show contours. Want to see the temperature, set it to local limits. Want smooth contours, apply. And you can see that how the temperature at that specific location looks like. Just rescale it. Of course, you can change the plane position by using this scale. So you can just move it down or move it up to see what the temperature looks like at that location. So let's just put it at 1.16. And we can see what the temperature looks like in the board region. Of course, this is a two-dimensional control plot, and you can change that to a three-dimensional control plot as well. So to do that, you can activate the show mesh object. Also go to parameters, and you can change the shading options to 3D, scale it, increase the scale, and we'll be using fixed values. Click on line, we will be selecting fixed values over here. Line color is fixed to a color which is black. Apply and done. So now you can see in terms of where the temperature is maximum, it will show you the trend in 3D plot. So it gives you a very good visual representation of the magnitude of the temperature at different location. Again, let's activate this. Now let's create another cut plane. Set the cut plane to z-axis and set it at 0.12. Show vectors. I want the velocity by default. This object and apply. Done. Let's increase the plane location a little bit. So you can see how the velocities look like. Now we can also cut out part of it. So we can clip it by changing these values. The y will be, let's set it to 50 minus 50 and update. And we clip out this portion, and you can look at only the velocity vectors at this location. So this is a very handy tool if you want to just look at a specific location, and you can essentially just clip it on an already existing solution. Now there are useful tools to see where the maximum and minimum temperature or any other solution parameter is present in the domain. So to do that, you can go to post, find min-max location, click on temperature, and it will tell you where the minimum temperature is and where the maximum temperature of the system is. Next is you can create a report summary. So go to report, summary report, set the name. The report face values will be selected. We have already created multiple objects. Essentially, to create objects, you will have to just select new and select anyone. Let's select the board, accept, and look at the temperature on the board, and it will automatically give you the solution order. Once you do that, you click on write, and it will give you a report summary data where you can see what is the min max mean temperature and of the object, maximum speed in the cabinet, minimum speed in the cabinet, the mean speed in the cabinet. Now let's activate radiation, because we see the temperatures are reaching almost 120 degrees centigrade. So maybe it's a good idea to add radiation to it and see if radiation is present in the solution, what will be the maximum temperature um, inside the cabinet. So we go to basic parameters and activate radiation. We are going to use the ray tracing radiation model, and we will use a coarse setting. So we'll just keep the flow iteration at 5, maximum radiation iteration to 5, set the faces to 20 and the resolution to 5 as well. Accept. Now we go back to solve, change the name, we will interpret the previous data, results, write overview and results file when the solution is finished, and we will start the calculation. So the calculation with radiation is computed, and we can see how the temperatures are lower than the case when there was no radiation. Also, if we create new temperature contour, you can immediately see how the temperature has reduced quite a bit because of the radiation. Now let's activate a failure possibility. So we go to fans properties, set it to failed. Clearly the next fan options failed. We also set our calculation laminar. Set up an initial velocity. But one setting, set the pressure discretization to body force average and tweak the under relaxation factors for better stability. Solve. You can see the solution has computed. And because of the fan failures, the cooling efficiency has dropped significantly. And we can see how the temperatures have increased significantly in this case. So you can see the maximum temperature for ADP has gone up by almost 150 degrees centigrade to 269. Um, Again, the DDR RAM temperatures have gone up by several notches to 150s range. The board temperature has gone up significantly. So it kind of showcases that when there is a cooling failure in the system, you can uh, have very high temperature, which will definitely lead to the failure of the whole component. With that, thank you for your time, and we will see you again in the next video. Bye bye.